Okay, maybe we should begin. Next talk. It's a pleasure to introduce my colleague, Jinxin Xue, Xue Jinxin. He's a Xiaomi Endowed Professor in the Department of Mathematics at Tsinghua University. Graduated in 2013 from University of Maryland under the supervision of Dmitry Dolgopiev. Huh? Yeah, Dima Dolgopiev. His field of research, dynamical systems, and Okay, please welcome. Oh, I forgot to say he is also winner of the 2024 Frontier of Science Award together for two papers. That's why there are like two talks, which actually it could have been one talk, but there are two papers that were cited, and it's the second talk where he will talk about his Frontier of Science Award. This is the first talk. He will talk about maybe some more recent stuff.
Okay. Yeah. Okay. Thank you, Ita, for the introduction. And yeah, thanks for explaining everything. So I'm supposed to give two talks. It's my pleasure to be here. Thank you very much for attending my talk. So the first one is about the mean curvature flows. It's more geometric flavor. And if you're really interested in dynamics, you will see some dynamics there. So let's start with the basic setting. So we consider a family of hypersurfaces in Euclidean space. So suppose suppose it's smooth at every point you can find the mean curvature, and at every point you have orthonormal. So you get a vector field on the surface. So hypersurface. So you form this this differential equation. So you try to evolve this manifold under this flow. It's called mean curvature flow. Basically, you expect that if the mean curvature is big, the flow is going to move faster, and if the mean curvature is small, then it moves slower. So you expect that the flow is going to make the manifold rounder and rounder. So that's the basic intuition. So let's give you some examples. The first example is the sphere. For a sphere, we know that at every point the mean curvature is the same. So under the evolution, the sphere is going to remain the shape of a sphere, but it's going to become smaller. So within finite time, it's going to vanish at some single point. This is the dynamics of a sphere under the evolution of the mean curvature flow. So for a cylinder, because it's the product of a sphere with some Euclidean space, so you expect that the spherical component becomes smaller, and within finite time, it's going to become some straight line, and it's going to vanish along the straight line. So the last example is the plane, because the mean curvature at every point is 0, so it's going to be just static there. So
question: how is this different from the Ricci flow?
Yes, this is the slide that I'm going to talk about. There are many similarities. So the advantage is that it's easier. So because of we know that Perelman solved the Poincare conjecture using the Ricci flow. So we expect that there's some parallel program for mean curvature flows. The main difference is that Ricci flow is about the intrinsic geometry. It does not care about if your manifold is embedded in some other manifold or not. But mean curvature flow is about the extrinsic geometry. So there are also lots of problems about embedded manifolds in geometry. We expect to use that to say something. Okay, so some toy model for the mean curvature flow was called the curve shortening flow. So you just consider some simple closed curve in R2, and every point you can compute the curvature, and you form this this differential equation. It's a classical and remarkable result that any simple closed curve can be evolved under this curve shortening flow until it disappears at some round point. That means the curve is going to become rounder and rounder. Finally, it's going to disappear. So this is very remarkable. It gives a flow proof of the Jordan curve theorem. And as we know that in topologies, the Jordan curve theorem is not easy to prove. So cartoon is like this. You can start with some simple closed curve that looks very complicated, but under the curve shortening flow, it's going to get simplified, and finally it disappeared at some round point. Okay, so now you expect that the same thing is going to happen for the mean curvature flow, but very unfortunately, it's not true. So there's a counterexample. In the higher dimensional case, if you start with this dumbbell-shaped manifold, because in the middle, the mean curvature can be very big, so it's going to move faster. So this middle part of the dumbbell is going to become thinner and thinner. So it's going to become to pinch within finite time. And after pinching, we know that the mean curvature flow is a heat flow. So the heat flow can immediately smoothen this manifold. So it's going to become some smooth manifold again. And under further revolution, each piece is going to disappear at the round point. So this is an example in higher dimensional case that shows you some new phenomenon that didn't appear in the two-dimensional case. So in general, all mean curvature flows develops singularity within finite time. So whenever you have a singularity, it's standard to blow up the singularity, try to analyze this local behavior. So we introduce another flow called rescued mean curvature flow. The point of the flow is that you add a term on the equation of the mean curvature flow. The behavior of this term is to expand the outside exponentially fast. So with the two behaviors together, you get this flow called rescued mean curvature flow. So it's very important that there are some remarkable monotonicity property of the rescued mean curvature flow. Basically, if you write down this functional on any manifold M, you evaluate at every point of the manifold locally, you evaluate the volume element with this Gaussian weight. This manifold, suppose it evolves under the rescued mean curvature flow, you look at the F functional under the evolution, you find that there is a minus sign. So if you compare this formula with this negative gradient flow equation, suppose some function f generates this negative gradient flow, you look at how the value of the function changes under the flow, you find that there's a negative sign. So with this similarity, you find that the rescued mean curvature flow is a negative gradient flow of the F functional. So that's where the technology of dynamical system enters. Okay, so imagine that suppose you have some differential equation. You want to understand its dynamics. The first thing you do is to find the fixed points. The next thing is that you linearize the equation around the fixed point. So to find the fixed point, you just set the right-hand side of the rescued mean curvature flow equation to be 0. You get this equation. So this any hypersurface satisfying this equation is called a shrinker. So if there were no this term, then you get h equal to 0. That's the equation for the minimal surfaces. So a shrinker has many similarity with the minimal surfaces. So whenever you have a singularity, you blow it up, you always find this object. So on the other hand, whenever you have a self-shrinker, it's going to produce a self-shrinking, a homothetic solution to the mean curvature flow equation. So they are very special solutions to the mean curvature flow equation. So we have to examine them first. Let's see some examples. There are actually people discovered many shrinkers. Let's start with this first, this compact example. So it's some it's a shrinker. It's some surface with some genus. The picture on the right is the one on the left cupped in the middle. So you can see a section of it. So you find that this shrinking cube is already quite complicated. So the one on the right is another non-compact example of self-shrinker. So in the middle, there is one genus, and asymptotically to infinity, it's approaching a cone. And the more complicated one here is, again, it's asymptotically conical. It's constructed by some, it's a very hard construction. But anyway, at this moment, we find there are many, infinite many shrinkers. So it seems impossible to understand them all. So by the way, I should say that studying mean curvature flow is in some sense equivalent to studying the rescaled mean curvature flow. Once you understand one of them, there is this equation to relate to the other one. Okay, as I said just now, there are infinite many shrinkers. It's impossible to understand all of them. So as dynamicists, it's really natural to think of if you can say what happens generically. So the idea of generic mean curvature flows already existed in the field of mean curvature flow, first proposed by Huisken and by Agnen, Eilmanen, and Trop, and other people. So let me briefly explain what's the idea of generic. So it's appeared in our course of analysis, maybe. So when we learned the concept of the bare second category set, there was this concept. So basically, you suppose you have some big parameter space. It can be infinite dimensional, and you look at infinite countable intersections of open and dense sets in that space. That's going to be generic a set of generic points. So the idea of studying this kind of thing is just because the object that we are studying is too complicated. In general, if you have a system that's very complicated and hard to analyze, you just try to ignore those very pathological cases, and by using just trying to say that what's the remaining stable behavior. So the openness part is about stability. The denseness part is about abundance. So that's the idea. But if you are not familiar with this concept, it's maybe it's good to remember the following example. That's going to occur repeatedly in the later part of the talk. So suppose I give you a matrix whose leading eigenvalue is simple and it's positive, let's say. And suppose, let's say its eigenvector is phi1. So the question is, how do you find the phi1? So just how do you find the leading eigenvalue and the leading eigenfunction? So the idea is that you can start with a generic initial vector v. So you only need to avoid the eigenspaces that's not corresponding to the leading eigenvalue. So that's you just need to avoid some hyperplane. Then you choose this v quite arbitrarily, and you iterate a to n times, and you normalize it. And in the limit, you are going to see this first eigenvector. So here, if you want to say something about any vector v, you have to classify all the possibilities. But here, if I just use the word generic, I can get this simple statement. So that's the idea of generic things in dynamics. Okay, so in the field of mean curvature flows, there are two major conjectures. One is called the Huisken conjecture. The conjecture says that if you consider generic mean curvature flows, that's going to simplify your understanding of shrinkers. Generic mean curvature flows should have only spheres and cylinders as the singularity model. So the next example, the next conjecture says that it's called the isolatedness conjecture. If you look at generic mean curvature flows, it's going to have only isolated singularities and isolated times. That means you only need to care about finitely many singularities. You don't have to worry about the accumulation of singularities. Okay, so I'm going to explain our work on the two conjectures. So first, the lying in the heart of all the studies are the two pictures. So for the picture on the right-hand side, you have a fixed point. The fixed point we think is the shrinker, and you try to linearize your flow near the shrinker. You get some linear equation. I'm going to show you the linearized operator in the next slide. So suppose the linearized operator has all the eigenvalues negative, then the fixed point is going to be stable. That means if you perturb the initial condition slightly away from the fixed point, under the flow is going to flow back to the fixed point. So, but the picture on the left-hand side is different. So on the left-hand side, you have, suppose you have one positive eigenvalue, and for other eigenvalues, you don't care. It can be positive or negative. But whenever you have one positive eigenvalue, the situation becomes unstable. Unless your initial condition is chosen on this y-axis in this picture, that means if you avoided this submanifold, that means you choose a generic initial point, your flow is going to flow away from the fixed point. So that's the basic picture for the instability. Okay, so how to understand the Huisken conjecture? So what should we expect if why should we expect it? It's important or it looks true. So let's compare with the classical picture from Morse theory. Suppose you have a function defined on a torus. Suppose it's good. It's a Morse function. You form the negative gradient flow. We know that it's going to have some critical points. So critical points of the F is going to be fixed point of the flow. So each one has some indices. So we know that, so this one is the stable one. So all the other three are unstable. So the point here is that if you avoid the stable manifold of the first three, that means there's some orbit that's going to converge to these fixed points. And in that case, we say the orbit lies in the stable manifold of that point. So if we avoid the stable manifold of the first three fixed points, so that's going to be some manifolds. So then for all the other points, that means for generic initial point, no matter wherever you are, so suppose you are here, then under the flow, you are going to all the way to the bottom. So that's going to be very remarkable because you get some results that's not obtained from local analysis. It's a global result. So the point of Huisken conjecture is like this. Suppose you know that the Huisken conjecture is true, then you only care about spheres and cylinders as your shrinkers. So then you start with any closed embedded manifold in the Euclidean space. If necessary, you add a small perturbation. So the flow is going to evolve it to some connect sum of spheres and cylinders after probably surgery. So that's going to be a remarkable result. It's going to say something about the topology of the embedded manifold. So that's the ultimate goal. So now let's try to do some analysis. As I said, whenever you have a fixed point, you try to linearize the system. So the linearized equation, the linearized operator is like this. So this L operator is like this. The first term is Laplacian. The second term is a drift term. So if you put the two terms together, it's called the Ornstein-Uhlenbeck operator from from probability theory. And the last term is about the geometry of the shrinker. Here, A is the second fundamental form. Okay, so we know the following things. The operator is self-adjoint with respect to this weighted inner product. And once you know a self-adjoint operator, you know that all the eigenvalues should be real, and there are infinite many negative eigenvalues. So because the problem appears from geometry, there are some eigenvalues. The first few eigenvalues carries clear geometric meaning. So first, there's an eigenvalue 1. Its corresponding eigenfunction is exactly the mean curvature. So this appears just because the flow is in some sense invariant under dilations. So on the other hand, you know that suppose you have a mean curvature flow, and this point you translate it to another point, it should still be the same flow. So this translation invariance gives you another eigenfunction. That's basically to project your normal vector to some fixed direction. So that corresponds to eigenvalue 1/2. Okay, there are also functions corresponding to rotations that I didn't list here, but the corresponding eigenvalue is 0. Okay, so the first result in this direction was proved by Cody and Minicozzi. They classified all the shrinkers with the mean curvature positive. These are exactly spheres and cylinders. So the observation is like this. Because the L operator is an elliptic operator, so we know that its leading eigenfunction has to be positive or negative. It cannot change sign. So I'm going to always say it's positive. Okay, so we also know that H, the mean curvature, is an eigenfunction. So if it's positive, that means it's the leading eigenfunction. Otherwise, suppose, according to the result of coding Minicozzi, suppose you have a shrinker that's not the spheral cylinder, then the leading eigenvalue has to be greater than 1. So because 1 is correspond to H cannot be positive at this point. So if your shrinker is not a spheral cylinder, the leading eigenvalue has to be greater than 1, and there should be some corresponding eigenfunction that's positive. So the basic idea is that this phi1 is our expanding direction, our unstable direction. So the idea is try to make a perturbation to move towards this phi1 direction in the function space. So that's the basic idea. So from here, you basically expect that there's a hope to perturb away all shrinkers that's not sphere or cylinder. Okay, so let me give you the first results. So actually, there's another group of people who obtain similar results with us, and actually the methods are totally different. That it turns out that at some point, from some perspective, their results are stronger. From some other perspective, our results are stronger. We use PDE method. I'm going to show you the idea. So the results are as follows. Suppose you have a mean curvature flow, which has a singularity. Suppose it has a shrinker that's not sphere, not cylinder. And there are two cases that we can handle. Either the shrinker is compact, and we can handle all the cases, or it's non-compact, but we need to assume that the shrinker approaches a cone asymptotically. Actually, these already include all the shrinkers that we know. The conclusion is that we can generically perturb the initial condition so that the perturbed flow avoids the singularity. So that's the result. Okay. Let me give you an idea. So suppose you have a flow MT which converges to a shrinker sigma as t goes to infinity under the rescued mean curvature flow. You know that the initial manifold M0 may be very far from sigma. So it may be impossible to put the two things in the same function space. Now we want to perturb the initial condition slightly so that the perturbed flow avoids the shrinker completely. So how to do that? So there are two steps. So suppose our initial condition is very small. Therefore, the perturbed flow is going to stay close to the unperturbed flow for a long time until the perturbed flow gets very close to sigma, gets to a small neighborhood. Okay, here the big circle is supposed to be a very tiny neighborhood. Okay, I'm just drawing that very exaggeratedly. Anyway, so after the flow enters a small neighborhood of sigma, we try to show that the flow is going to leave the neighborhood along the phi1 direction. So that's the basic idea. The question is how to realize this picture. So there are basically two ideas. So the first one, if we consider the piece of orbit getting close to the shrinker, because the manifold becomes close to the shrinker, we can write the manifold as a graph of some function over the shrinker. So we get the mean curvature, the rescaled mean curvature flow can be written in the following form. It's some nonlinear equation, but you have a linear part that's given by the L operator, and there's also a nonlinear part. So the next idea coming from dynamical systems is that you can basically ignore the nonlinearity. So suppose you just draw some cone centered around the phi1 direction. So this horizontal axis, you imagine that's phi1. Suppose you have at some point your orbit enters the cone, lies inside somewhere in the cone. Then under the flow, because in the phi1 direction, it's correspond to the leading eigenfunction. So you look at the exponential of the solution to this equation. You should look at the exponential of LT. So it looks like applying the action of this map. So horizontally is expanding exponentially, and in other directions, it either contracts or expands slower. So therefore, the cone is going to become narrower and narrower. So that means if your orbit stays in the cone for a long time, it's going to get very, very close to phi1 direction. So if you are close to the phi1 direction, then you are going to leave the neighborhood. So that's the local analysis. It's some standard technology from dynamical systems. Okay, so the next question is how to care about this, how to take care of this red piece. So the idea is as follows. Again, we try to linearize the flow along the unperturbed manifold, along the unperturbed flow. Because if my initial perturbation is very small, that means the two flows are very close. Therefore, I can always consider the perturbed flow as the graph over the unperturbed flow. So again, linearizing the perturbed flow along the unperturbed flow, I find the linear part and the quadratic part. So I'm going to focus first on the linear part. So it's something quite familiar to geometers. It's called the Jacobi field equation if you are in the finite dimensional case in Riemann geometry. So we are going to use this linear heat equation to control the red piece. So now the problem is that how to send an initial perturbation into a cone around the phi1 under the evolution of the variational equation. So we have to analyze what does it mean by a function lies in the cone. So we know phi1 is some positive function with it's just some positive fixed function. So we suppose you have some function u. We want to say that u lies in the cone. That means u, when projected to phi1 direction, the projection should be lower bounded. So that's the equation here. So now you only need to find some sufficient condition to guarantee this equation. So one condition that you can imagine is that if you can guarantee that your function u does not oscillate much. For instance, if your function u is satisfies some uniform derivative bound, then you find this equation, this inequality has to be true. So now it comes the famous Liao estimate from differential geometry. So for any positive solution of this heat equation, we can bound the solution at earlier time by the solution at a later time. But very unfortunately, here we really need some derivative control or oscillation estimate on the same time slice. But the Liao estimate can only give us estimate for different time slices. If your T1 gets close to T2, then the constant C blows up. So it's not applicable directly. So the idea is to play with some trick like energy estimate. It turns out it's possible because we know that energy estimate is to control a later time by earlier time. Therefore, we successfully get some estimate. It's called Harnack estimate on the same time slice. So with this, we complete our reasoning. That's the basic idea for the first work. So we wrote basically 2 papers on the Huisken conjecture. So let's next talk about the isolatedness conjecture. So suppose the philosophy of the Huisken conjecture is that you only need to care about spherical and cylindrical singularities. Suppose it's true, even though we know a lot in dimension 3, but for higher dimensional case, it's still widely open. But anyway, we want to proceed assuming the Huisken conjecture. So if we assume the Huisken conjecture, we only need to care about the spherical and cylindrical singularities. But the spherical singularities are always isolated, so you don't need to worry about that. So you only need to care about cylindrical singularities. So what can you say? So there, maybe let me skip this slide. There's an example in the field that's an example with a continuum of cylindrical singularities. So the model is called a married ring. It has some rotational symmetry. It's just like this. You evolve this manifold under the mean curvature flow. Within finite time, it's going to disappear along a circle. So if you blow up every point, each point at the circle, you are going to see a cylinder. So that's the basic idea. And every point is the same because there's the rotation symmetry. So this is a good example of no isolatedness. So we try to understand what happens to this model. So again, we need to analyze the linear equation. So the linearized operator has the following list of eigenvalues and eigenfunctions. So the first eigenvalue is 1. Here, the ck is the same as sigma k. The first eigenfunction is also 1. That's the mean curvature. So the next eigenvalue is 1/2. There are 2 types of eigenfunctions. So the first type is theta I. Theta I is just to restrict the coordinate function on the spherical component. So that corresponds to spherical harmonic functions. But anyway, so this theta I corresponds to translations in the spherical direction. And there's also translation in the Euclidean direction. We call it yj. So y means coordinate in the Euclidean direction. So the next eigenvalue is 0. So there are 2 types of eigenfunctions. The first one is to just multiply the 2 things. So this theta I yj, that corresponds to rotations. And as I said, we have this Euclidean isometry or dilations. All these things are not geometric. They cannot change the geometry of the manifold. It's better that you find some way to get rid of them. So the non-trivial thing is mainly this y squared minus 2. So it's some parabola. So you imagine that in the Euclidean direction, you have some parabola, and you rotate it around the spherical direction. You find that locally your manifold so has some thin part. So that's going to be responsible for the isolatedness. So the first theorem that we prove is that suppose you have a mean curvature flow with cylindrical singularity, then you look at how the flow approaches the singularity asymptotically after modulo translation and dilation, modulo all the Euclidean things. What you get, the first non-trivial thing you get is like this. So as t goes to infinity, it decays linearly, and there are some yi components. Here, this index set is a subset of this list of numbers from 1 to k. So now there are basically two cases. We introduce the notions. We say a singularity is non-degenerate if the set of indices is exactly from 1 to k. It's everything. Otherwise, we call it degenerate. Actually, I recently found it's really some important concept here. Anyway, so the first result we prove is as follows. Suppose you know that your singularity is non-degenerate, then it's stable. That means if you have a non-degenerate singularity, then if you perturb initial condition slightly, there's still, for the perturbed flow, there's still such a non-degenerate singularity. Okay. The second theorem said that non-degenerate singularities are dense. That means if you do have a degenerate one, then you can find an arbitrarily small initial perturbation so that the perturbed flow has a non-degenerate one. So if you put the two things together, that tells you that non-degenerate singularities are generic. And also you know that, as I said, non-degenerate means that you have some parabolic behavior. In particular, if you look at this normal form that we get, it's some normal form that works for radius of square root t, of size square root t. If y is of order square root t, y squared is of order t. That means this function is going to be of order 1. So that's already tells you that inside some region of size order 1, you just have one singularity. That means we also have a result saying that non-degenerate singularities are isolated. So in order to prove the isolatedness conjecture, the best way, the easiest way I expect is just to prove the non-degenerate singularities are generic. But anyway, so maybe let me give you some idea of, before going to the idea, let me state another result. This one is more global because the last two results were about the rescaled mean curvature flow, but this one was really the mean curvature flow. So you just consider the model of the measured ring. So the theorem says that we can perturb the initial condition slightly. The perturbation can be very, very small. And after the perturbation, the perturbed flow is going to have only one singularity. The place of the singularity can be prescribed. You just give me any point on the singularity set, and I can find the initial perturbation to produce one singularity close to that point. So that's one global result that we proved. But anyway, maybe in the last few minutes, let me briefly explain what's the idea in the proof. Actually, it's some easy, very easy analysis. So the idea is try to get non-degenerate normal form. So now we here H2 is just this y squared minus 2. We just abbreviate, call it H2. It means the second Hermite polynomial. So here, let me briefly explain to you what's the main difficulty. The problem here is that the H2 is the eigenfunction with the eigenvalue 0. There are still eigenvalues above 0. So H2 is not a leading eigenfunction. So if you just make initial perturbation, it's very likely that your perturbation under some terms of evolution is going to go to those eigenspaces spanned by 1 theta I or yj, but not H2, because H2 has smaller eigenvalues. So now the idea is just try to always use Euclidean rigid transformations to get rid of these growing faster modes. Now the problem is that you can use dilation to get rid of 1. You can use translation to get rid of theta I. You can use rotation to get rid of this guy. But this one is very tricky. In general, it's not possible to get rid of them. So the key observation is that you just try to add some perturbation with a non-trivial H2 mode. Then once you have this thing, then you are in good shape. The reason here is that you can always make a small translation in this function. You find by completing the square, you get some term 2a yi. So now suppose you have already some yi component that's non-vanishing. You just choose your a to get rid of it. That's the key idea, the key observation that we made in the paper. So whenever there's some non-trivial y mode, that's dangerous for you because the corresponding eigenvalue is large. The flow is most likely to flow to that direction. But your idea is that you try to make a translation to get rid of it. So you just do infinite many steps of translations. Along the flow, whenever you see a yi component, you make a translation to get rid of it. Then you flow further. If this yi component appears due to the nonlinearity again, you just make a further translation to get rid of it. Then you keep doing that for infinite many steps. Eventually, you don't have to worry about that. So this is the key idea that appears in the proof. Maybe I think my time is almost out. Yeah, maybe in the last slide, let's make a dictionary relating geometry and dynamics. So as I said in the talk, so the rescued mean curvature flow can be considered as the negative gradient flow. So from this perspective, every object in geometry has some corresponding thing in dynamics. So for instance, shrinker is considered as fixed points, and there are stable shrinkers. They are things. There are unstable shrinkers. They correspond to hyperbolic fixed points. And in dynamics, there's a concept called invariant manifolds. Actually, correspondingly in geometry, there are also that concepts. And the next one, it's a typo. I should switch the two columns. So in geometry, there's a notion called ancient solution. And in dynamics, we call it orbits on the unstable manifold. So we have this geometric heat, this heat equation, linear heat equation. So in dynamics, that's the Jacobi field. And also, the last thing, the leading eigenvalue of the L operator on the shrinker, that's the top Lyapunov exponent in dynamics. So I think maybe let me stop here. Yeah, okay. Thank you very much.
Thank you for an elucidating talk.
My next talk is about the n-body problem. So there's the slide.
Okay, second dictionary. Okay, are there any questions?
Thank you for your talk. Are there some parallel results for the mean curvature flow in hyperbolic space?
There are people doing that. Yeah, there are people working on that. I'm not into that. Yeah.
Oh, thank you.
Yeah. Okay. Thanks for your question. Yeah, it's very new. I think very few papers on that subject.
Can I ask a question about the conjectures? Are there any specifications of the topology on the space?
The space of hypersurface.
Yeah.
Yes, you can give C1, C2.
Does it specify any?
I think if it's more than C2, then they're all the same.
What do you mean they're all the same?
I mean, it does not really matter because the heat flow quickly smooths your manifold. So the heat flow, you can start with some, Dirac delta function. The heat equation quickly gives you some analytic function. So yeah. In general, we just start with C2 in order to define the mean curvature. Then immediately it becomes C infinity.
I see. Any more questions? If not, let's thank Professor Jinxin once again.
Yeah, thank you. Good. It's